In the last video, we showed how a surge tank or a storage tank behaves as an integrator. The integrator is the type of transfer function that we obtained when analyzing the model of the surge tank in the Laplace domain. In this video, we'll introduce a model that gives rise to a transfer function that we call a first-order transfer function. Consider this mixing tank, and suppose we want to know how the effluent composition X changes in response to changes in X1, the composition of incoming stream 1. The species balance on the solute says that the accumulation of solute in the tank is equal to the rate at which solute enters the tank minus the rate at which solute leaves the tank. We can define deviation variables, just like we did for the storage tank, and write the steady state version of the species balance by replacing the accumulation term with 0 and replacing each of the variables with their steady state values. We'll assume that W1, W2, and X2 are constants. Then we subtract the steady state equation from the dynamic equation to write the dynamic equation in terms of the perturbation variables. Finally, we take the Laplace transform of this model. Notice that because we wrote this model using the deviation variables in the time domain, the term W2 times X2 minus X2 goes away. Because W2 and X2 are constants, they do not deviate from their steady state values, and therefore their deviation contributes nothing to the deviation in X. X1 is changing with time, and X is changing with time, so those two variables both have non-zero deviations that contribute to the rate of the deviation of X. When we take the Laplace transform of the derivative of the perturbation variable, the initial value of the perturbation variable is 0 if that perturbation variable begins at the steady state value. Now we can solve this Laplace domain equation algebraically for the transfer function relating x prime, the deviation in the composition of the effluent, to x1 prime, the deviation in the composition of incoming stream 1. And we find a transfer function that has a first-order polynomial in S in the denominator with a constant term of 1. The transfer function that we define as G1 here describes how changes in the incoming stream composition X1 affect the effluent stream composition X. In this case, our model has only one input variable, X1, and only one output variable, X. But now, suppose X1 and X2 are both allowed to vary with time. Then we can write an additional deviation variable, X2 prime, and now our time domain balance equation for X should contain terms with both X1 prime and X2 prime on the right-hand side. When we take the Laplace transform of this dynamic equation, we now have two transfer functions, each relating the effects of an input variable to an effect on the output variable. We call these two transfer functions G1 of S and G2 of S. Both of these transfer functions have a constant K1 or K2 in the numerator. When the denominator constant is equal to 1, we found the constants K1 and K2 by dividing the numerator and denominator by the constant term W, so that the constant term in the denominator was equal to 1. When the transfer function is written with the constant term in the denominator equal to 1, then the magnitude of the numerator is called the steady state gain. The steady state gain tells us by how much a deviation in the input variable will affect the deviation in the output variable when the system reaches the new steady state. In this case, changes in X1 will affect changes in X by an amount K1 X1 when the system reaches a new steady state, and changes in X2 will affect changes in X by an amount K2 X2 when the system reaches a new steady state. Both of these transfer functions also have a time constant in the denominator multiplying S. In this case, that time constant for both transfer functions is the residence time of the tank, rho v by W. That time constant determines how quickly the system will reach the new steady state in the time domain. Both g1 and g2 in this example are called first-order transfer functions because the denominator is a first-order polynomial in S with a constant term. These do not behave the same as an integrator, as we'll see later. Before we compare their behavior, in the next video, we'll introduce a model that gives rise to what we call second-order transfer functions.